Hello and welcome back. In the previous video, we talked about the history of the Kalman filter, and also I shown you the magic equation of the Kalman filter. What was that? The magic equation of the Kalman filter says that the true state of any system is equal to its model prediction, which is uncertain usually, and we update that model prediction using the weighted difference of the sensor data and the output corresponding to the sensor data which is coming from. And also I mentioned that this Kalman gain is the main thing that we have to calculate in the Kalman filter. It will be updated in each iteration, and it takes into account the modeling error and measurement uncertainty. But how? To show you how to calculate this Kalman gain, we need to know one more basic regarding the Kalman filter. And it is the Gaussian assumption. What it means? It means that every quantity of interest in the Kalman filter follows a normal distribution. It means it has a mean and variance. And if it is a vector, we are working with vectors. We have a vector as a mean vector and a covariance matrix for that, this multivariate distribution. It means, okay, now we can relate this x with the mean of this normal distribution I talked about. Then this equation, this true state is the mean of the states. And this is the mean of the predicted state. And this is the mean of the predicted output. But what about the variance? We cannot put aside the variance of that predicted state or output. And how we let the other parameters, the variance of the state and the measurement, plays their role in the algorithm. And those variants which represent the uncertainty of the prediction helps us to calculate this Kalman gain. But how? We see it right now. To drive the algorithm of the Kalman filter, we work with the state space representation of the dynamical system. And what it says for any dynamic system, for example, x hat at n plus 1 is equal to a xn, and which we call it transition function. And we have y hat n plus 1, which is equal to c x hat n plus 1, which is the measurement function. Usually, as I said, the model is not accurate. We usually have the modeling. Then we add one white noise term here, which we call it xvn, which follows vn is a white noise with a normal distribution, which has a mean of 0 and variance or covariance matrix of q. And for this measurement function, we have a noise term, which we call it measurement error. And this term also has a normal distribution with mean of 0 and variance of r. Okay, then these q and r represent the modeling error and measurement uncertainty of the system we are working with. Okay, then now we have everything we need to write down the Kalman filter algorithm. First of all, we have to predict the mean of the states. Then I say step 1 is the mean of the state is a xn, which xn is the true state from the step n, which we use to predict the state at time n plus 1. Because the mean of this v is 0, it doesn't have any effect on the mean value of the predicted state. But now we have to calculate the p. Then we say the p of I call it p hat n plus 1 is equal to x hat n plus 1 minus the mean of the x hat n plus 1 times x hat n plus 1 minus x hat mean n plus 1 transpose. And if we substitute axn here, we get something like a x minus x bar n x minus x bar n transpose a transpose. And what is this? This is the variance of the true state, which is coming from the previous time step, and we call it P.Eng. Then we have something like this, a P.N. A transpose. And what I do here, I add this Q term to the predicted state variance. I call it plus Q. What happens here is something like this. You see the yellow curve, the yellow bell shape is this term. Once we add the Q to this predicted state variance, it gets wider. It means that, and we work with this blue curve, and that is the modeling uncertainty incorporated in the model prediction. We do the same thing for the output as well. Then this is the equation to calculate, to predict the output, the mean of the output, which is y hat at time n plus 1 is equal to c x hat n plus 1, which is the predicted state. And we follow the same procedure we did at state 3 to predict the variance of the predicted output, which we call it Sn at time n plus 1 is c p hat n plus 1 C transpose. And what I do here, I add R, which is my measurement error, to this predicted output variance. And as I showed you here, we incorporate the measurement uncertainty in the predicted output variance. Okay, now we predicted the mean and variance for the states, the mean and variance for the model output. Then okay, we completed the distribution. We completed the calculation process of the predicted state and predicted output. Then in step 5, we use these Sn and P hat and C to calculate the Kalman gain. And the Kalman gain, which I call it Kg, is equal to P hat n plus 1, which represent the uncertainty of the model prediction, times C transpose divided by S n plus 1. And as I said in the previous video, Kalman gain has a direct relationship with the modeling error and inverse relationship with the measurement error. And if you want to see how this Kalman gain is calculated and where does it come from, I put my PhD thesis, it's linked in the description of this video, and you can see the details and mathematical concept behind it and how you can drive it. And using this Kalman gain, we go to step 6. I'm going to write it here, step 6. And we right now we are in a stage that we can calculate the true state in step n plus 1. Then the true state at time n plus 1 is equal to the model prediction at time n plus 1 plus Kalman gain, which we calculated just here, times sensor data, the difference between sensor data and model prediction of the output, which we call this term innovation term. Okay, then we saw that how using this Kalman gain, we saw that how can we calculate this Kalman gain using the modeling, incorporating the modeling error and measurement error, which I've shown you how to calculate. And this is, as I said, this is the mean of the true state. But what is the variance of the true state? And that goes to step 7, which gives us the P of the true state, which is equal to I, which is the unit matrix, minus K, which is Kalman gain, times C, which is the measurement matrix, times P hat n plus. Okay, this is the whole process of the Kalman filter algorithm. If I want to explain it and look at it, not from a mathematical point of view, is that you have a mathematical model, which I showed you here. This is the transition function, measurement function. You predict the mean and variance of your model prediction. You calculate the mean and variance of the model output. You use the variance of the predicted state and the output to calculate the Kalman gain, which balance that how much you trust your model prediction or your measurement prediction, and use this and incorporate this into the magic equation of the Kalman filter to update the state, the predicted state. And after that, calculate the variance or uncertainty of your Kalman filter update. That's the whole process of the Kalman filter. Before jumping to the examples and show you how to use this Kalman filter algorithm, I need to mention 2 points. Kalman filter is a Bayesian algorithm. It means you need to have a initial knowledge or prior knowledge about the system. Then, for example, if once we want to start the algorithm, this n is equal to 0, for example, if I want to write it here at step 0, n is equal to 0, then you need to have a true state, x0 and p0. These two are your prior knowledge about the system. These two are your prior knowledge about the system, which you use it, for example, here to calculate the variance of the prediction, or you use it here to calculate the mean of your predicted state in the first stage. Another point I want to mention is, again, I'm going to come back to this magic equation. Once we are talking about the filter, Kalman filter, this filter is a different word, has a different meaning than once we say a low-pass filter or high-pass filter, which we exclude specific frequencies from a signal. Here, the filtering means that if we have a prediction at time n+1, we use data at n+1 to update or correct the model prediction. Okay, then this is the meaning of the filtering here. Once we say prediction, we say we use data at time n to predict something at time n+1. This is a prediction problem. But for filtering, we use data at time n+1. We use data at time n+1 to correct the model prediction at time n+1. Okay, here we use data to predict something at time n+1. But for filtering, we use data at time n+1 to update the model prediction at time n+1. Okay, this was the second point I was going to mention before going to implementation phase of the Kalman filter algorithm.